Okay, this is going to be our 6th video in our electric charge and electric field series. In the last video, we spent the whole video looking at the electric field outside of a uniformly charged line segment, right? And we took a look at what it would be like very close to that line segment and what it would look like very far from that line segment, right? So that kind of gave us well, in the case of very far, it gave us back our electric field outside of a point charge, and very, very close, we were kind of looking at the electric field outside of an infinitely long line segment, right? So in this video, we're going to take a look at the electric charge of a uniformly charged ring, and this is example 21.9 from the text. They don't really go into very much detail as they do it. I'm gonna go into a little bit less detail in this one than we did in the last one, because we've already seen sort of how some of this stuff works. So I'm just going to hit the key highlights, but I'm also going to take a look at the integral that we want to do here. So we want to make sure that we can do all these integrals. And well, I guess let's just get right into it here and see how this is going to go. Okay, so we have the charged ring here in front of us. The point that we're interested is this point P, so we're interested in the electric field at this point P. And it's important that the point P is on the axis of our ring, right? So if we drew a line out from the plane that the ring sits in from the center of the ring, this is the point. Well, this is where the point is located, right? And so we start off first by let's start off by writing down our charge density, right? So we have lambda, and lambda is going to be equal to Q. This is the total charge on the ring over the sort of length of the ring, and in this case we're dealing with a circumference because it's a ring. So it's going to be 2 pi a, where a is the radius of our ring, right? So we have the charge distributed over 2 pi a of length in the circumference of our ring. Again, we know that we need to find dE, and this is going to be equal to k dq over r squared, right? This is our small segment of this is a small contribution to the electric field that we want to find, right? So last time we went to all the trouble of sort of calculating what the contribution would be in the y direction, and then finding out that it's 0. Here we can kind of see a few things just by inspection, right? So what are we expecting? Well, we're expecting only to find an electric field contribution in the direction of x here, right? So in the I hat direction. We're expecting that all the j hat, or all the y direction electric field is going to cancel, because as we go around the ring, we can imagine that this electric field would be pointing in a bunch of different directions, and they should all cancel out, right? So we should only find an electric field pointing along the I hat direction. And so I'm just going to sort of write that out here. We're expecting that E at P, which is equal to EX at P I hat, plus EY at P J hat, plus EZ at P K hat, is going to have a Y, well, an EY component of 0 and an EZ component of 0. So this is just going to be EX at P I hat. Okay, so we only have to worry about calculating that one quantity. And then what do we expect this quantity to sort of do? So once we find our answer, how can we double check this? Well, if we think about it, let's say we slid P all the way back and we were sitting in the very center of the ring. What do we expect to see our electric field doing there? Well, at that point, all the contributions are coming from sort of in the plane here, and we would expect everything to cancel out, right? There would no longer be an x component, and all the y components and z components, as we're sort of coming out of the paper here, would cancel out, right? And so we would expect to see, maybe I'll write this down. So we would expect that for x going to 0, we expect E at P, so as P slides into the center of the ring, we expect this to be 0 also. And then, what else do we expect? for x much, much larger than the radius of our ring, we would expect, again, to regain the electric field of a point charge, right? So if we think about it, if we get really, really far from this ring, we would expect that the electric field at that point would look very much like that of a point charge, right? We're very, very far. We can't really see the ring anymore, so it's kind of like a point charge. Okay, so let's do the calculation and see if this is actually what we end up with. Let me draw some lines here, and let's get started here. So we need dEx, and we can see again the same way we argued before that our dE in the x direction is just going to be dE cos theta, right? Or I guess in this case cos alpha, and I might have labeled it theta last time also, but really it's cos alpha, because I mean alpha is going to be changing as we're going around the ring, right? And so we can just substitute in this dE information that we have up here. So what is that going to be? Well, that's going to be k cos alpha over r squared dq, right? But we know that r squared, maybe I'll write a little closer here, we know that r squared is equal to x squared plus a squared, right? Because of what we have up here. And so we can make that substitution. Let's do that. We can see that k cos alpha, this is going to become k cos alpha over x squared plus a squared dq, okay? But then also cos alpha, because we're dealing with a right angle triangle here, right? This is a right angle triangle. We can make a simplification that cos alpha is just going to be x over the square root of x plus a, right? So I'll write that here. Okay, and if we make that substitution, we're going to end up with k dq over x squared plus a squared x over square root x squared plus a squared, okay? And the final thing that we're going to want to do is we're going to want to replace this dq using our charge density, right? And so if this was the case here, we can sort of see what we wrote up here. We're going to write dq in terms of lambda, our charge density, times a small segment of length around the circle. Okay, so ds is very similar to what we used before dy, right? So we're kind of working our way around the circle, taking tiny little sections of length as we go around the circle, and those are our ds's. Okay, so I'm going to rewrite one more time. Maybe I'll write it over here. This is going to be k lambda x over x squared plus a squared to the 3 over 2 ds. Okay, and so this is going to be the quantity that we want to integrate, and we want to integrate this quantity around the whole circle. Okay, and so let's take a look at that here. We're going to want to integrate. We're going to want to integrate from 0 to 2 pi a. Okay, and that's the full circumference of our circle, right? So because our radius is a, 2 pi a will be the full circumference of the circle, so we want to be going from 0 all the way out to 2 pi a, okay? And let's write that integral out. So we're going to see that ex is equal to the integral of dex, and we know that, and I'm going to write it in terms of a definite integral, so we're going to see that we can factor a bunch of this stuff out. We're basically only integrating over s, and so basically everything comes out. We're going to see that it's going to be k lambda x over x squared plus a squared, to the 3 over 2. And then we want to do the integral from 0 to 2 pi a of ds. Okay? But this is a pretty simple integral for us to do. We're just integrating ds. So the indefinite integral of ds is just s. And so if we take the limits at those points, this is 2 pi a. And if anybody's not really comfortable with the sort of speed that that was done at, I would encourage you to sort of go back, take a look at how these integrals would work, and make sure you're comfortable with it, okay? And so what does this give us? This means that well, we're kind of done, right? So this means that we have our answer. We know that our electric field at point P is going to be equal to what we just calculated, Ex at the point P pointing in the I hat direction. And we just saw that that is k lambda x over x squared plus a squared to the 3 over 2. And we now have a 2 pi a here, and this would all be in the I hat direction. Okay, and we can kind of clean this up to get a form more familiar, or at least more commonly written down. So I'm going to use the fact that lambda times 2 pi a is q. Oops, I should have an equals there. Is q, right? So this is just the circumference times our charge density is going to give us back the charge, the total charge on the ring, right? So if we use that, so if I substitute that back in, that's going to let us write that our electric field is equal to k q x over x squared plus a squared to the 3 over 2 in the I hat direction. Okay, and that is the equation that you'll usually see, or you may see k change into its 1 over 4 pi epsilon naught form, but basically this is the electric field outside of our charged ring along its axis, so along this x-axis that we've drawn here at any distance x, and that's our expression. So let's take a look at what we were talking about before. Do we regain what we expect if we let these numbers run? So let's say at x equals 0, right? What do we get? What do we get when we let x equal 0? Well, we can see right away that x going to 0 implies that, well, our upstairs is going to go to 0, and so this whole thing goes to 0, right? It implies that the electric field at x equals 0 is equal to 0. Okay, and for the same reasons we talked about before, right? At the very center of the ring, all these contributions cancel out, and we end up with no electric field at that very center point. Okay, and what happens if A is much smaller than x? Right? If A is much smaller than x, I won't actually do the sort of taking of the limit here, but you can kind of see that A is basically going to go to 0 here, and we can kind of divide this through and do it more formally, but just by looking at it, you can kind of see that A is going to go to 0. You're going to end up with an x squared to the 3 over 2, so you're going to end up with an x cubed in the basement. It's going to cancel with the x above, and you're going to end up with an electric field for x, or I should say for A much less than x. We're going to see that our electric field looks like this. It's going to look like k q over x squared in the I hat direction, and this is exactly what we would expect for a point charge sitting at our origin here for some p way out in the x direction, right? And that would be that result. Okay, so this was the first example I wanted to do in this video. We're now going to take a look at a charged disk. Okay, and I'm going to pause the video for a second here to draw the whole thing up. I don't have a drawing down here, but to save time, I'll pause it and we'll get back to it in 1 second here. Okay, so this is the setup for the disk that we're going to be looking at. So we're now going to be looking at a uniformly charged disk along its axis, and it's kind of nice that we just did the ring, because our approach here is going to be to use our ring result, and maybe I'll write down the ring result right here. So we have our ring result that we generated up here. We're just going to copy that down here, and we saw that e to ex we saw that this is our result here. Right, for our ring. So now what we're going to want to do is we're going to take this ring result, and we can imagine, instead of integrating around the circle, we're going to integrate in, like, up along this line, but we're going to be integrating this circle result, basically building these concentric circles of thickness dr, of this infinitesimal thickness dr, and we're slowly going to build a ring out of it, right? So we'll start from a radius of 0, so just a point, which will be what happens if we let a go to 0 here, and then we're just going to build it all the way out until we build our entire disk of radius r, right? So we have a disk, the full radius is r, capital R, and we're going to be integrating over all these tiny little drs until we build all these concentric circles all the way out to the outer edge of our disk. Our disk is going to carry a charge of q, and the charge density is going to be given by sigma here. This is because we're dealing with a surface, so this is that sigma that we talked about a couple of videos back, right? And so basically we can get right down to it here. So we're going to be interested in integrating just this. Well, again, so we can argue away all the other contributions. We know the only contribution that's gonna play a role here is in the I hat direction. So we need to look at Ex, and just pulling out the scalar portion of the above expression. We're gonna have Qx over x squared plus a squared, the 3 over 2. And so this is our expression for one ring, and now we just want to integrate over all rings that make up this surface, right? And so what's sort of going to happen here? Well, let me box this off. We know that here our dq, our small chunk of charge, is really going to be sigma times dA. So it'll be our charge per unit area times a little chunk of area, okay? But we know that the circumference of our circle is 2 pi r, right? And these r's will be changing as we sort of increase the size of the ring that we want to look at, okay? And the thickness of the rings are going to be dr. So we have circumference here and thickness here, okay? And this means that our dA is really going to be, well, it's going to be basically our circumference times some small chunk of thickness, right? So we're going to have some small chunk of thickness that we're working with as we go around each of these concentric circles, right? And this means that our, I'll write it here, this means that our dq is going to end up being 2 pi sigma r dr, okay? And if it isn't obvious why that sort of is, take a second here, maybe pause and think about how all these components come together. We have our circumference, the thickness of our ring. We know that sigma times dA gives us the full charge, and well, okay, yeah, sigma times A would give us the full charge, but sigma times dA gives us some small chunk of charge, and we want this small chunk of charge written in terms of dr, because we're going to be integrating over r as we increase the size of these rings that we're looking at, right? And so if we just take this above expression and substitute in dq for our q, and we let a go to r, and why are we doing that? Because before we had our ring of radius a, but now our ring size is going to be varying as we integrate across all the concentric rings that make up our disk, right? So we let a go to r, we end up with an expression that looks like this. And there's going to be a bunch of stuff on top. It's going to be 2 pi sigma r dr, and there's still a leftover x from before, and then in the basement we're going to have x squared plus what's now r squared to the 3 over 2. Okay, and so this is the expression that we really need to be integrating. What we want to do is we want to solve the integral ex, and I'm gonna factor everything out that flows through the integral here. We're going to have 2 pi sigma x k, and we're going to be integrating from 0 out to r, right? And why are we doing that? Again, because we're taking the tiniest ring at the very central point, and then all the concentric rings that go all the way out until a radius of r, and we need to integrate r dr over x squared plus r squared to the 3 over 2. Okay, so this is really the expression that we want to solve to get our electric field at the point P. So let's do that. We're going to take a look at that integral here. I have it here. Yep, perfect. Okay, so let's take a look at just the indefinite integral that we need to solve. We need to solve the integral I is equal to r dr over x squared plus r squared to the 3 over 2, and then we're going to worry about doing the definite integral after we have the solution. Okay, so to do this, we're going to let t equal x squared plus r squared, and if we do that, this means that dt is equal to 2r dr, and we can kind of rearrange this into the form that we want. We want r dr, and we can see that that's going to be equal to 1/2 dt. Okay, so we can substitute in for our top here and our bottom. So if we do that, we can see that I'll put this all in brackets. So we're just going to apply all these ideas, and I is going to end up looking like this. It'll end up being dt over 2t to the 3 over 2. We can factor out that factor of 1/2, and since we're going to be employing the sort of power rule here, I'm going to rewrite this as a negative power. So this is going to end up being t to the minus 3 over 2 dt. Okay, just doing that integral, we're going to end up with 1/2. We'll have a minus 2 t to the minus 1/2. And cleaning this up, we end up with minus t to the minus 1/2, which we can rewrite as so I'm going to move the t into the basement and the square root, but I'm going to replace the t with x squared and r squared. So it's going to end up being minus 1 over square root x squared plus r squared. Okay, and now we can bring this back into the sort of language of a definite integral, and we end up with ex equal to 2 pi sigma x k, and this is just me substituting this information back into our definite integral up here, right? And we just did this one, so we're going to end up with minus 1 over square root x squared plus r squared, which all needs to be evaluated from 0 to r, right? And we can do that right here. We can see that we can pull out the minus sign. We're going to end up with a minus 2 pi sigma x k, and then our first term is going to be r, so we're going to substitute r in for lowercase r here. We're going to end up with 1 over square root x squared plus r squared minus, and if we substitute in 0 for lowercase r, we're going to end up with a 1 over square root x squared. Okay, and this we could simplify into a 1 over absolute x. Okay. Now what can we do here? We can let's pull out an x here in the basement to simplify this whole thing. So okay, so how are we going to do this? Let me rewrite this here. Ex is going to be equal to, and maybe, okay, so we're going to want to keep this, okay, so I'm going to rewrite it one more time so we can keep this all in order. I'm going to slide the minus sign back inside here, and we're going to end up with a 2 pi sigma x k, and now we're going to end up with, in the brackets, 1 over absolute x minus 1 over square root x squared plus r squared. Okay, so let's keep this one in mind. We're going to need to make use of this expression in a minute, but this isn't the final form. I mean, this is a final answer, but we're going to clean it up for our result of the disk here. So what I'm going to do is I'm going to factor out an x in the basement here, and so that means that we're going to have to hit the upstairs of this with an x, and so we're going to end up with an ex equal to 2 pi sigma k, because the x's will cancel, and we're going to have a 1 minus x over square root x squared plus r squared here. Okay, and we can use the fact, it'll actually clean it up a fair bit if we use the fact that k is equal to 1 over 4 pi epsilon naught. Substitute that in there. We'll get rid of the 2 pi, and our k will be gone, obviously, so we're going to end up with an ex equal to sigma over 2 epsilon naught 1 minus x over square root x squared plus r squared. Okay, and I'm going to do one more substitution here, or simplification, so that we can take a look at some of the limits of this afterward. But I'm just going to multiply the bottom here by x over x. So I'm basically just multiplying the bottom by 1. And if I do that, I can eliminate the x's upstairs here, right? So I can do this, and then I can move this x inside the square root by squaring it, and we're going to end up with an expression that looks like this. Maybe I'll rewrite it fully. It's going to look like this. And it may actually look messier than it did before, but okay, we don't need all this extra space. But this is going to let us see the limit a lot more easily. Okay, so let's use this as our final answer here. This is our the x component of our electric field outside of our charge disk, and we could write this in vector form just by hitting it with an I hat in front of it, but we don't really need to for right now. What we're going to do for right now is we're going to take a look at some of the limits as we get very, very close or very, very far from this thing, right? So which one did I do first here? Charge at large x. Okay, so let's take a look at the charge at very, very large x. Okay, this one's a little harder to see than the very small x, but I think it's worth going through. I don't think the text does it, or at least doesn't do it explicitly, so we're going to kind of go into a little bit of detail here. But let's take a look at this expression here. Which one did we have? This one that I have boxed here. Okay, so I'm going to rewrite it here. We could again do this substitution of k for 1 over 4 pi epsilon, and we would end up with an expression that looks like this. So we're going to have ex, and maybe I'll do a little bit of a title here. Look at large x, and this is going to give us a point charge. Okay, so we're going to look at large x, and we're going to see that it's going to give us back our result for a point charge. So what are we doing when we're looking at large x? Our point is floating off to the right here, and we're getting farther and farther from the disk, so it's looking more and more like a point charge, and we hope to see a point charge, right? So like I said, we can manipulate this expression that I have in the dotted box pretty easily here to give us back this expression here. This is just substituting in for k, the 1 over 4 pi epsilon naught. And if we do that, we end up with this. Okay. And let's just take a look at the term in the brackets here. So we're going to want to take a look at this as x is much, much greater than r. It's kind of hard to see what this what the limit of that would kind of look like. Okay, and I don't want to do a formal limit here. We're just gonna kind of work our way through it and see if we can just pick it off. So what do we have here? I'm just looking at the term. Well, let's call this A, and I'm just looking at A here. So A equals 1 over absolute x minus 1 over square root x squared plus r squared. And that's going to be equal to square root x squared plus r squared minus absolute x over absolute x. I'm just getting them over the same denominator here, so we're basically just cross multiplying, right? And I don't like this this square root in the upstairs, so I'm going to multiply by the conjugate. So basically, this equal sign here, what I'm doing is I'm just multiplying top and bottom by x squared plus r squared plus absolute x, right? So I'm just multiplying by 1 by multiplying top and bottom by this. So if I do that, the cross terms are going to cancel, and on the top we're going to end up with x squared plus r squared minus x squared. Okay, and if that was sort of too quick, I encourage you to multiply the top and see how that turns out. In the bottom, we're going to end up with what we had before, x squared plus r squared in the square root, times now square root x squared plus r squared plus absolute x. Okay. I guess I won't bother rewriting it, but we can see that these two terms will cancel. And we're now in a pretty good sort of shape here to see what happens. So look at x much greater than r, right? So what would happen? What would happen if x was much greater than r? Well, all these terms, so this would imply that all these terms that look like x squared plus r squared are going to go to absolute x's, right? Because we're going to end up with the r basically going to 0. It won't contribute much, and we're going to take the square root of x squared. That's just going to give us absolute x, okay? And so what does a end up becoming? So a will then end up going to, well, we're going to have an r squared in the top, which will be small, but it's still there. It's the only thing in our numerator. And what are we going to have in the bottom? Well, we started off with an absolute x. This square root here is going to give us another absolute x, and we're going to end up with an absolute x plus absolute x. And what does that look like? Well, that's just going to look like r squared in the upstairs and a 2 absolute x cubed in the basement. Okay. And so let's rewrite this and take a look at what our electric field, or at least the x component of our electric field, which is all of our electric field, is going to look like at well, is going to look like for x much greater than r. So we're going to end up with sigma x over 2 epsilon naught. And what do we have with our, what we call term a here, or the factor a? We're going to have an r squared over 2 absolute x cubed, right? So one of these x's can cancel out one of these absolute x's, and we end up with something that looks like this. Okay, and we're not quite there yet, but we're getting there. We're hoping to end up recovering our point charge, and we will here. The way we're going to do this is we're going to see that it's true that for our charge here, our charge is actually equal to sigma pi r squared, right? And let's think about why that's the case. This sigma, this is our charge per unit area. And what's the area of our disk? Well, this pi r squared is the area of our disk. So we can see that pi r squared, pi capital R squared times sigma gives us back q. Okay, so let's substitute in for that. So we're going to end up finding that sigma is equal to q over pi r squared. If we make that substitution, we're going to find that Ex is equal to q r squared, and I'm going to change the Oh no, we already have it changed. Okay, perfect. Yeah, so I'm just going to rewrite it this way. 4, I'm going to move the pi and the r squared downstairs, so we're going to have pi, I'll keep an epsilon naught in between, r squared, x squared, right? These r's are going to cancel, and we're going to end up with an expression that looks like this. I'll rewrite the ex here, so ex is equal to 1 over 4 pi epsilon naught q over x squared. Okay, and I mean we could see this as a k, but basically this is the electric field outside of a point charge, where the point charge is sitting at the origin and we're sitting on the x-axis, right? So that's exactly what we expected to find. One more result that we want to get at here, and yeah, I think I have space here, so we will do it right here. We want to take a look at, and this is kind of why so this boxed off one that I have up here was a sort of version that was easiest to work for to regain the point charge. We're going to work with this one that we've kind of manipulated to the point where we can take a look at r much greater than x more easily for what happens when we get up really close to this disk, right? So let's take a look at the disk. Let's imagine now that we're moving our p closer and closer in until we're right up against the edge of this thing, right? So what would it look like as we're right up against the edge of it? Well, it would basically look like an infinite plane almost, right? And of course, again, there's no such thing as an infinite charged plane, but this is a good approximation to being close to a very large charged plate when you're right up against it, right? So let me start by rewriting our electric field of our disk. We have this expression here, 1 minus 1 over square root r squared over x squared plus 1, right? And now what we're going to basically do is we're going to look at r much greater than x. And if we do that, we can see that this term that goes like this, the term that goes like this is going to end up going to 0, right? Because we're going to end up with a very large r here, right? And we're going to be so this plus 1 won't matter. We're going to take this, we're going to square it and take the square root of it. So we're going to be dividing 1 by some very large number. Basically, this is just going to give us no contribution at all. So it's just this 1 that's going to dominate. And so what does this mean? Well, this means that our ex is going to go to sigma over 2 epsilon naught. Okay, and this is a very important result. This is the result for the electric field outside of an infinitely charged plane that you're sitting next to. Now, one interesting thing about this result is that it has no x dependence, right? And so that's kind of weird. But what we've really calculated here is if we had a truly infinite plane, what would the electric field be like outside of it? Well, it wouldn't matter how far you were from it, because no matter how far you were, the plane would always look infinite. So everywhere the electric field is the same. Doesn't matter how far you are from it. There's no x dependence. And that's the sort of result that we're getting here. Obviously, again, no such thing as an infinitely charged plane, but this gives us a good approximation when we're close to the plane and it looks infinite. Okay? And so that's where we're going to leave this one. The textbook does have one more example that you guys can work through on your own with 2 charged plates. It's a good example as well. These, I can't really stress enough how important these examples are. This example of the charged rod, the charged ring, and the charged disk are some of the really sort of central key examples of this entire course. If you can do these, if you can do the integrals involved in these, you're already well on your way to understanding a lot of the material that we're going to be covering in this course. And it sort of comes up very early in the course here, so don't let yourself fall behind here. Like really go through these. Make sure you fully understand these. If you don't, come and talk to me. I'm more than happy to help you out or go through them again. But these are really super important examples. Okay, so I'll leave it here, and I'll see you guys in the next one.